Hey everyone, and welcome. Today we're going to be building your very first chemistry toolkit. Think of these as the absolute essential tools you've got to have to really understand how the world of atoms and molecules works. So let's get right into it. You know, this quote really nails it. Everything around us, everything in chemistry, it's all built from these tiny things called atoms and molecules. But here's the catch. They're ridiculously small, and there are billions and billions of them in even the tiniest speck. So, the big question is, how on earth do we actually work with them?
So here's our game plan. First, we'll talk about the main challenge. Then, we'll start adding tools to our toolkit. We'll get a tool for weighing things we can't see, a tool for counting them in huge groups, a tool for reading chemical recipes, and finally, we'll figure out what to do when one of our ingredients runs out before the others.
And that brings us to the core of the problem, right? The whole puzzle of chemistry is figuring out how to deal with things that are completely invisible. We need a way to measure and count them before we can do anything else.
So let me just ask you directly. Can we see, weigh, and count individual atoms one by one? The short answer is no way. Not a chance. Just to give you an idea, a tiny 2-gram sample of hydrogen gas has more than 600 sectillion molecules in it. That's a 6 with 23 zeros after it. You're never going to count that. So chemists had to get creative.
And that's where our very first tool comes in, since using grams or kilograms would give us these insane, tiny numbers with tons of decimal places. Chemists just invented a whole new unit, specifically for atoms. It's called the atomic mass unit, or AMU for short. Okay, so here's the key thing to get. An AMU is just a standard that scientists all agreed on. They basically picked one very specific atom, carbon-12, and said, all right, this atom right here, we're going to say it has a mass of exactly 12 AMU. That means 1 AMU is just 1/12 of that carbon atom. It gives us a nice, simple scale to compare all the other atoms to. This analogy is absolutely perfect. You know, the kilogram wasn't some magical unit we discovered in nature. We just made it up. People picked a specific chunk of metal and said, this is 1 kilogram. And that's exactly what chemists did with the carbon-12 atom. We just picked a starting point so we could start weighing the invisible.
But wait a second, there's a little wrinkle here. Out in nature, it turns out that not all atoms of an element are identical. Some are a little bit heavier or lighter than others. We call these isotopes. So, if they have different masses, what number do we actually put on the periodic table?
Let's look at chlorine. It's a great example. You can see that about 76% of all chlorine atoms are the lighter kind, chlorine-35, and the other 24% are the slightly heavier chlorine-37. They have different masses. So to get the single number for the periodic table, we can't just pick one. We have to calculate a weighted average.
And here's exactly how you do it. Let's walk through it. For step 1, you take the mass of that first isotope, 34.9689, and multiply it by its abundance, 75.77. Then you do the same thing for the other one, 36.9659 times 24.23. For step 2, you just add those two big numbers together. And finally, for step 3, you take that total and divide it by 100. And what do you get? 35.5 AMU. And that is the exact number you'll find for chlorine on the periodic table. See? We just weighed the invisible. Okay, awesome. Tool 1 is in the bag. We can now weigh atoms. But we still need a way to count them. And since we already said we can't count them one by one, we're going to have to count them in really, really big bunches.
Get ready for a number so big it's hard to even imagine. This is Avogadro's number. The easiest way to think about it is like this. It's the chemist's dozen. You know how a dozen is always 12? Well, when a chemist wants a bunch of atoms, our bunch is always this enormous number. This is our second tool.
And this special chemist's dozen has a name. It's called the mole. So if I tell you I have 1 mole of water, it just means I have Avogadro's number of H2O molecules. This idea, the mole, is the critical bridge that connects the tiny world of single atoms to the world of grams that we can actually weigh out on a scale in the lab.
So, how do we figure out how many moles we're dealing with?
There are a few different ways, but we're going to focus on the one you will use 99% of the time. The one that connects the mass of something to the number of moles.
All right, this formula right here, this is a big one. You're going to use it all the time. Moles is simply the mass you have in grams divided by something called the molar mass. So what's molar mass? Easy. It's just the atomic mass from the periodic table, but instead of saying AMU, we say grams per mole. So for CO2, we just add up the pieces. Carbon is about 12. Oxygen is about 16, and we have 2 of them, so that's 32. Add 12 and 32, and you get a molar mass of 44 grams per mole. That's it. And that's why if you have 88 grams of CO2, you just do 88 divided by 44, and you get 2 moles. Simple as that.
Fantastic. Okay, we can weigh atoms and we can count them using moles. Now we get to do the really fun stuff, chemical reactions. And for that, we need our third tool, stoichiometry. It's a really fancy word, but all it means is learning how to read a chemical recipe. Seriously, that's all it is. A balanced chemical equation doesn't just tell you what ingredients you need, it tells you how much of each ingredient you need. And the secret is in those big numbers written in front of each molecule. That's the ratio.
Let's look at a classic recipe, burning methane. See those big numbers? They tell us the mole recipe. For every 1 mole of methane, we need exactly 2 moles of oxygen. And when they react, we'll produce 1 mole of carbon dioxide and 2 moles of water. And here's where it all comes together. We can use our molar mass tool to convert that mole recipe into a gram recipe. 1 mole of methane is 16 grams. 2 moles of water is 36 grams. This lets us see exactly how much stuff we're making.
So, let's try a quick question using our recipe. If you start with exactly 16 grams of methane, how many grams of water are you going to get out at the end?
You got it. 36 grams. The recipe is crystal clear. 16 grams of methane in, 36 grams of water out. Stoichiometry lets us predict exactly what's going to happen. It's incredibly powerful.
Okay, but let's be realistic. When you're in a lab, or even just cooking in your kitchen, you almost never have the perfect amounts of every single ingredient, right? So what happens when you have too much of one thing and not enough of another? That brings us to our last big idea. This is the perfect way to think about it. Imagine you're trying to make sweet milk. You have a ton of milk, 10 whole liters of it, but you've only got 2 spoonfuls of sugar. What's going to run out first? The sugar, right? It's obvious. No matter how much milk you have, the sugar limits how much sweet milk you can possibly make.
And that is exactly what a limiting reactant is. It's the ingredient, the reactant, that gets completely used up first. It stops the reaction and it determines the absolute maximum amount of product you can create. Everything else is just left over.
So let's end with one last challenge to put all your new tools to the test. Look at this reaction. The recipe, the balanced equation, tells you it's a 1-to-1 ratio. For every 1 mole of A you need, you also need 1 mole of B2. But look at what you actually have. 2 moles of A and 3 moles of B2. Okay, think it through with me. To use up all 2 moles of your A, how many moles of B2 would you need? Well, 1-to-1, so you'd need 2 moles. Do you have enough? Yeah, you have 3. Now let's think about it the other way. To use up all 3 moles of your B2, how many moles of A would you need? Again, 1-to-1, so you'd need 3 moles. Do you have enough? No, you only have 2. So which one is going to run out first? Thinking through problems just like that is the key to mastering all of these basic concepts.